All right, let's dive in. Today, we're going to pull back the curtain on one of the most clever and kind of hidden problems in all of artificial intelligence. It's all about how the AI that's literally all around us learns to deal with something it has never, ever seen before.
I want you to picture this for a second. You go to type a totally unique sentence on your phone, something creative, maybe a little weird, and it just freezes up. It refuses to finish the thought because in all the trillions of lines of text it's been trained on, your exact phrase has never existed. I mean, that sounds completely absurd, right? But this is the fundamental crisis that early language AI faced every single day. And the math behind this is actually dead simple. See, a language model figures out how likely a sentence is by multiplying the probabilities of each word showing up in order. But what happens if just one of those combinations has never been seen before? Well, its probability is 0. And as you can see right here, anything, and I mean anything, multiplied by 0 is 0. The entire sentence, poof, becomes mathematically impossible in the eyes of the AI. This catastrophic glitch actually has a name, the zero probability problem. And this is really the villain of our story today. It all comes from this one simple but totally fatal assumption that if something wasn't in the training data, well, it can never happen. And when you're dealing with something as messy and creative and unpredictable as human language, that is a recipe for absolute disaster. And look, this is a true disaster. It's not just about a buggy keyboard. It means the model has no ability to generalize. It's incredibly fragile. It breaks the second it bumps into the real world. Even the tools we use to grade an AI's performance, things like perplexity, which is just a fancy way of measuring how surprised a model is by new text, they become completely useless. A model that assigns 0 probability to a sentence that's perfectly valid isn't just a little bit wrong, it's fundamentally broken. So how in the world do you fix this? Well, enter the hero of our story, a whole family of statistical tricks known as smoothing. And the name is just perfect because that's exactly what it does. It's all about smoothing out those sharp, disastrous zeros into something, more realistic. It's about teaching the AI a little humility, teaching it to accept that, hey, maybe it hasn't seen everything the world has to offer. The core idea behind it is just brilliantly simple. You can almost think of it like a wealth tax, but for probability. Smoothing techniques basically take a tiny, tiny fraction of the probability owned by all the common, frequently seen word pairs, and they redistribute it. They give a sort of universal basic income to every single word combination that has never been seen before. This makes sure their probability is super small, but crucially, never ever 0. Now, there wasn't just one way to pull this off. Over the decades, researchers came up with an entire toolkit of smoothing techniques, and each one was a little cleverer than the last. So let's take a quick tour and see how the thinking on this really evolved. The very first attempt, called Laplace smoothing, was basically just adding 1 to every count. It's a bit of a blunt instrument, to be honest. It often gives way too much probability to the unseen stuff. Then, more sophisticated methods came along, like Good-Turing, which had this really clever insight. It uses the number of things that happened only once to predict what hasn't happened at all. And then you have absolute discounting, which created a really simple and effective foundation that other, more advanced methods were later built right on top of. One really intuitive strategy that came out of this is called back-off. It's a simple if-then kind of logic. So the model first tries to use its most specific knowledge, like, what's the probability of the word cheese following the phrase, I like grilled? If it's never seen that 3-word combo, it doesn't just give up. It backs off to a simpler model. It just checks the probability of cheese after the word grilled. It's a really graceful way to fail, falling back on broader knowledge when the super specific stuff isn't there. Now, a slightly different and often more powerful approach is called interpolation. See, instead of choosing one model and then backing off if it fails, interpolation creates this weighted average of everything at once. It takes a little bit of predictive juice from the 3-word model, a little from the 2-word model, and a little from the single-word model, and it blends them all together from the start. This constant blending makes the final prediction a whole lot smoother and more reliable. Okay, so all of this evolution, all this trial and error, it led to what became the gold standard for an entire generation of language models, Kneser-Ney smoothing. And it was built on this one truly profound insight. What really matters isn't just how often a word appears, but how many different kinds of ways it appears.
And this example just nails that core idea. Okay, take the word Monday. Sure, it might show up a lot in your data, but it almost always comes after the word on. It's kind of predictable. Now compare that to the word the. It shows up after thousands upon thousands of different words. So if you had to bet, which word is more likely to appear in a completely new, totally unseen context? Kneser-Ney correctly puts its money on the, because its history proves it's way more versatile.
And that right there, that focus on contextual diversity, is what made Kneser-Ney so incredibly powerful. It was just amazing at handling the zero probability problem for rare words, and it had a rock-solid mathematical foundation. For years, years, if you were building a serious language model, this was the technique. It was the undisputed champion of the world. So that brings us to the modern era, right? We've jumped from those classic models to the massive neural networks we have today. The transformers, the GPTs of the world. So what happened to smoothing? Does your phone, right now running the latest and greatest AI, have a little Kneser-Ney algorithm chugging away inside it to stop it from freezing up? The answer is a big, fat no. But, and this is where it gets really cool, the problem didn't just vanish into thin air. The solutions just went underground. They got baked directly into the architecture and the training process of the models themselves. You could say the ghost of smoothing is still in the machine.
See, modern models solve this problem implicitly, in a bunch of clever ways. Take word embeddings. They represent words like king and queen as being close together in space. That lets the model generalize what it knows about king to make smart guesses about queen, which is effectively sharing probability. Other things, like regularization, basically punish the model for being too overconfident, which discourages those extreme 0 or 1 probabilities. And of course, when you train a model on pretty much the entire internet, truly unseen events get a whole lot rarer to begin with.
So you might be thinking, okay, if the old formulas are gone, why did we just go through all that? And it's a fair question. But understanding smoothing isn't just a history lesson. It's about getting at a fundamental principle of machine learning. How do you gracefully handle uncertainty and generalize from the little bit of data you've seen to an infinite world of possibilities? This quote from the source material just says it all, doesn't it? The challenge of bridging that gap between what a machine has seen and what is possible is absolutely timeless. Smoothing was the first really brilliant solution to that problem, and its spirit, its core idea, lives on in the very DNA of every large language model we use today. And that leaves us with one final thought to chew on. These systems were built to handle unseen words, but what about unseen ideas, unforeseen consequences, novel situations that these AIs will face as they get woven deeper into our world? It really makes you wonder, what are the next big zero probability problems that we haven't even thought to solve yet?